Question: draw a circle and two lines parallel to a given line such that one is a tangent and the other is a secant to the circle. For this, first we have to draw a circle. Using a compass, you all can draw a circle whose center is at O. Then draw a line that will be the given line. We will take PQ as the given line. Draw a straight line passing through the center or at any point. Then to this we have to draw two lines parallel to this given line such that one will be a tangent. So, parallel to this line, if we have to draw a tangent, we can draw the line touching the circle only at one point. Suppose at this point, if we draw a line, this line should be parallel to this PQ like this. We can call this line as AB. So, AB is the tangent to this circle. We can call this point of contact as C. So, AB is the tangent which is parallel to this given line PQ. If we have to draw a secant, secant should be a line which touches the circle at 2 points. So, and it has to be parallel to this given line also. So, we will draw it on this side. We will draw a straight line which cuts the circle at 2 points. We will call this as XY. Now, XY is the straight line which touches the circle at 2 points. Therefore, this will be called as a secant to the circle. Therefore, we have drawn a circle and there is a given line PQ in the circle which is already present. To this line, we have to draw one line parallel and it should be a tangent. So, AB is the line parallel to the given line PQ and it touches the circle at one point C. Therefore, AB is the tangent. We have drawn two lines, one is AB, that is the tangent, and the other line should be a secant. We will draw a line XY which touches the circle at 2 points. So, XY will be called as the secant to the circle, and this is how you have to draw the lines to the circle in this. Now, to find the number of tangents that can be drawn to a circle from a point on the circle. For this, we will consider three cases. One case when the point P lies inside the circle, and one case when the point P lies on the circle, that is on the circumference of the circle, and the third case is when the point P comes outside the circle. Point P is outside the circle. You can see that when the point P is inside the circle, if you draw any line, it will touch the circle at 2 points. So, it cannot be a tangent. So, a tangent is a line which touches the circle only at one point. So, for any point which is inside the circle, you cannot draw tangents. They will all become secants. So, in the first case, when the point P lies inside the circle, we cannot draw any tangents to the circle. In the second case, when the point P lies on the circumference of the circle, we can draw only one tangent, because at any point on the circumference of a circle, we can draw only one tangent to the circle at that particular point. So, in the second case, we can draw one tangent. Now, if the point P lies outside the circle, that is the third case, from the point P, if you draw any line, you can draw a number of lines to touch the circle, but we will see that only one line will touch the circle at one point, and in the other direction when you draw, there also it will touch the circle at one point. So, we can draw maximum two tangents from a point P which lies outside the circle. From that point to the circle, we can draw two tangents. From a point outside the circle to the circle, we can draw two tangents. Therefore, to sum it up, in the case when the point lies inside the circle, we cannot draw any tangents to the circle from that point. When the point P lies on the circumference of the circle, we can draw only one tangent, and from a point which lies outside the circle, we can draw two tangents and not more than two tangents to the circle from that point. So, this is the number of tangents that can be drawn to a circle from any particular point, if it is inside, on the circle and outside the circle. Next, we will start with a theorem. Theorem number 2 in circles. the statement of the theorem is the lengths of tangents drawn from an external point to a circle are equal. Now we will consider this circle with center O and P is an external point. From the point P we have drawn two tangents, PQ and PR, where it touches the circle at Q. One tangent touches the circle at Q and the other one touches at R. According to the theorem, we have to show that these two tangents PQ and PR are equal. We have to show that PQ is equal to PR. For that, we will join the P to O, we will draw PO and we will join the center of the circle to this point Q, and from the center to the point R we will draw lines and we will join that. Now we will see that in this figure we have two triangles. One is triangle OPQ and the other one is triangle OPR. So in these two triangles OPQ and OPR, that is in triangles OPQ, one is the triangle OPQ and triangle OPR, we can see that OQ is equal to OR. OQ and OR are equal. So what is OQ? OQ is the line between the center and that point, and OR is the. Why are these two lines equal? We have to write the reason for this in the brackets. Why we are writing this as equal? The reason is that both are the radius of the same circle. So OQ is also the radius, OR is also the radius. So we can write they are the radii of the same circle. So that is the reason why OQ is equal to OR. Next, in these two triangles, OP is the common line between them. So OP is there for one triangle and OP is the side for the other triangle also. We can write OP is equal to OP. So here OP is one side of this upper triangle and OP is a line that is there for the lower triangle also. So OP is equal to OP means it is a common side to both the triangles. So OP is the common side, that is the reason. And also from theorem 1 we have shown that this angle OQP and angle ORP both will be 90 degrees because they are the angle formed between the radius and the tangent. The angle between the radius of a circle and the tangent will always be equal to 90 degrees, that is according to theorem number 1. So angle OQP is equal to angle ORP and both are equal to 90 degrees. This is from theorem 1. From theorem 1 we know that they are 90 degrees. Now considering these three, that is two sides and one angle of the two triangles are equal. So when two sides and one angle are equal, we can say that the two triangles are congruent. Therefore triangle OPQ is congruent. This is the symbol we use to say that they are congruent. Congruent means they are equal, is congruent to triangle OPR. So the two triangles are congruent. When the two triangles are congruent, we can say that PQ is equal to PR. Therefore PQ is equal to PR, and the reason for this we will write as CPCTC. This means corresponding parts of congruent triangles are congruent. This is the short form we write for this. This will be given in the textbooks also. CPCTC means when we prove that two triangles are congruent, their corresponding parts also will be equal. Corresponding parts of corresponding triangles are congruent. Therefore, the two triangles are congruent. We can say that their corresponding sides PQ and PR are the corresponding sides for the two triangles. They will also be equal. Once again I will tell, the PQO and in triangle OPR and OPQ, we will take the two triangles and we will prove that they are congruent. For that, first of all, these two sides OQ and OR, they are equal because they are the radii of the same circle, and the center line OP is a side that is common to both the triangles, and this angle here OQP and this angle ORP, both are 90 degrees. That is from theorem 1, because angle between the radius of a circle and a tangent will always be 90 degrees. So, those two angles are 90 degrees and those two are equal. Therefore, these two angles OQP and ORP are equal, both are equal to 90 degrees, so they are equal. Now, we have shown that two sides and one angle of a triangle are equal. Therefore, the two triangles are congruent. When two triangles are congruent, we can say that the corresponding parts of corresponding triangles are congruent, that we write as CPCTC, and therefore, we can say that the corresponding sides PQ and PR are equal to each other. Therefore, according to the theorem, the lengths of the tangents drawn from an external point to a circle are equal. Both the tangents will be of equal length. PQ is a tangent and PR is a tangent, which are drawn from the external point P to the circle, and both the tangents will be equal in length. So, this is the proof, and we can write this as proved. So, students, in circles we will do some example sums. Consider this. Prove that in two concentric circles, the chord of the larger circle which touches the smaller circle is bisected at the point of contact. In this, what is given is there are two circles. What do you mean by concentric circles? First of all, concentric circles means circles which have the same center, common center. So, that is they are called concentric. Here C1 and C2 are two circles in which O is the center for both the circles. We have to show that the chord of the larger circle is C1 and AB is a chord of C1 because it touches C1 at 2 points A and B. We have to show that this chord, if it touches another smaller circle C2 at one point P, it is bisected at this point of contact. Bisected means dividing into two equal parts. That means if AB is cut into two equal parts at the point P, then AP should be equal to BP. That is, this part and this part should be equal. We have to prove that AP is equal to BP. In this, we will consider the smaller circle C2 first. This is AB is a chord to circle C1 because it touches C1 at 2 points A and B. At the same time, it is touching the smaller circle C2 at the point P at one point. So, we can call AB as a tangent to circle C2. So, because AB is a tangent to C2, if we draw a line from the center to the point of contact, that will be the radius, and according to theorem 1, this radius and the tangent are perpendicular to each other. That is, this angle OPB over here, the angle will be 90 degrees. So, we can say that OP is perpendicular to AB by theorem 1. You have to write the reason in the brackets. According to theorem 1, OP is perpendicular to AB. Now, we will consider the bigger circle and we will imagine that this smaller circle is not there. If you have this bigger circle C1, AB is a chord to C1, and there is another property which says that a perpendicular drawn from the center of a circle to a chord will bisect the chord. That is, perpendicular from center of a circle to a chord will always bisect the chord. Now, because this we have shown that it is perpendicular, OP is perpendicular to AB. Now, this perpendicular to AB is drawn from the center to the chord. According to this property, that OP will bisect AB. Therefore, we can say that AP is equal to BP. So, this is what we have to prove. They have given two circles. One is the bigger circle C1 and the other one smaller circle C2. In this we have to show that the chord of the bigger circle which touches the smaller circle at one point P is bisected. Bisected means it is cut into two equal parts at P. If P, that means P will be the midpoint of AB, then AP should be equal to BP. That is what we have to prove. Then we will take the smaller circle, and AB, which is a chord to the bigger circle, is also a tangent to the smaller circle. And according to theorem number 1, the radius of the circle at the point of contact with the tangent is perpendicular to the tangent. That is theorem 1. According to theorem 1, we can say that OP is perpendicular to AB. Now, according to another property, a perpendicular drawn from the center of a circle to a chord of the circle will always bisect the chord. So, according to that property, you can say that because AB is a chord of circle C1 and OP is the line drawn from the center to AB, it will be perpendicular to AB and therefore it will bisect AB. Therefore, we can say that AP is equal to BP. This is the proof for this example. So, students, we will do one more example in this circles. The question is, two tangents TP and TQ are drawn to a circle with center O. So, this is the circle, center is O. From the point T, that is external point T, to this circle, they have drawn two tangents, one is TP and the other one is TQ. We have to prove that this angle PTQ, PTQ is this angle, is twice of angle OPQ, OPQ is over here, that angle. So, we have to prove this. Now, we will consider this angle PTQ to be equal to x. Let angle PTQ be equal to x. Now, from theorem 1 we can say that this TP is equal to TQ. Sorry, from theorem 2, that is tangents drawn from an external point to a circle are equal to each other. We have proved that theorem. So, according to theorem 2, TP is equal to TQ, that is according from theorem 2. Therefore, since TP and TQ are equal, we will consider the triangle TPQ, this triangle TPQ. This will be an isosceles triangle because two sides are equal in that triangle. Therefore, triangle TPQ is isosceles. What is an isosceles triangle? A triangle in which any two sides are equal is called as an isosceles triangle. If these two sides are equal, then these two angles also will be equal. This and this, we will call them as y. Both will be equal to y. Therefore, this is angle TPQ is equal to angle TQP, and both of them we will call it to be equal to y. Now, when we add all these three angles, it should be equal to 180 degrees. So, we will add that angle in this triangle TPQ. In triangle TPQ, angle PTQ plus angle TPQ plus angle TQP, the three angles in this triangle. This is angle PTQ, this is TPQ and this is TQP. If you add all these three angles, it should be equal to 180 degrees according to, that is called as angle sum property of triangles. Angle sum property of triangles. According to that, therefore, now we have taken PTQ to be x, x plus TPQ is y, and this also is y, is equal to 180 degrees. So, this becomes x plus 2y is equal to 180 degrees. Now, take x to the right hand side, 2y is equal to 180 degrees minus x. Now, you divide the right hand side by 2, take this 2 to the right hand side, becomes y is equal to 180 by 2 minus x by 2. So, we can say y is equal to 180 divided by 2 will be 90 degrees. This is 180 degrees divided by 2 is 90 degrees minus x by 2. This we will call as equation number 1. Now, next we will consider this angle OPT. What will be the angle OPT? According to theorem number 1, it is the angle between the radius and the tangent. Angle between the radius and the tangent will always be 90 degrees. Angle OPT is equal to 90 degrees. This is from theorem 1. According to theorem 1, angle OPT is 90 degrees. But here we can see that this angle OPT is nothing but OPQ. This angle plus this angle. Two angles are added to get OPT. So, we can write OPT as angle OPQ plus angle QPT or TPQ is equal to 90 degrees. Now, angle OPQ we do not know, plus we know that QPT, this one, this angle QPT is y. OPQ plus y is equal to 90 degrees, or angle OPQ is equal to 90 minus y. You take y to the right hand side, becomes 90 minus y. Then we will substitute for y from equation 1. From here, y value is 90 minus x by 2. We will put this 90 minus x by 2 in this equation. Then we will get angle OPQ is equal to 90 minus, for y we will write 90 minus x by 2. 90 minus x by 2. So, here it is 90 minus y. For y we have substituted this value as 90 minus x by 2. Then we will get OPQ is equal to 90 minus, when you open the bracket this becomes minus 90, and minus into minus becomes plus x by 2. 90 minus 90 is 0. So, we get angle OPQ is equal to x by 2. So, what is x? X is nothing but PTQ. So, we can say that this angle OPQ is equal to angle, for x we will write PTQ, angle PTQ by 2, or if you take 2 to the other side, we will get twice angle OPQ is equal to angle PTQ, and that is only what we have to prove. Twice angle OPQ is equal to PTQ. So, this is what we have to prove, and the given question is proved. Now, in this they have given that from the point, from an external point T, they have drawn two tangents. One is TP and TQ to a circle with center O. We have to show that the angle PTQ, this angle is equal to this twice of this angle, that is OPQ, twice OPQ. For that we will consider PTQ to be x, angle of PTQ to be equal to x. Then according to theorem 2, tangents drawn to a circle from an external point are equal. So, the two tangents TP and TQ will be equal. Therefore, if two lines are equal, if you consider the triangle TPQ, it will be an isosceles triangle. In that, if it is an isosceles triangle, these two angles also will be equal. So, we will take those two angles to be equal and let them be equal to y. Next, we will consider the triangle TPQ. We will add all the angles in a triangle. When you add all the angles in a triangle, it should be equal to 180 degrees. That is called as angle sum property of triangles. So, we will write down what we have taken PTQ, that is x, and TPQ and TQP, those two angles we have taken as y. X plus y is equal to 180 degrees. Next, y plus y is 2y. So, x plus 2y is 180 degrees. Take x to the right hand side, then it becomes 2y is equal to 180 minus x. So, y is equal to, you take 2 to the right hand side and divide each term by that. So, 180 by 2 and x by 2. 180 by 2 you will get as 90. So, y is equal to 90 minus x by 2. We will take this as equation number 1. Next we will consider this angle OPT. This angle OPT is equal to 90 degrees according to theorem number 1, which says that the angle between the radius and the tangent will always be 90 degrees. So, this angle OPT can be split into OPQ plus QPT, two angles. Here in OPT you have OPQ plus QPT, two angles are there. So, we have written OPT as OPQ plus QPT angles is equal to 90 degrees. Then OPQ is what we have to find out, QPT is equal to y we have taken. So, angle OPQ is equal to, you take y to the right hand side, it becomes 90 minus y. Then from equation 1 we will substitute the value of y and we will get OPQ is equal to 90 minus, this y is 90 minus x by 2. When you open the bracket it becomes 90 minus 90 plus x by 2. 90 minus 90 is 0. So, angle OPQ is equal to x by 2. So, angle OPQ is equal to x value is PTQ. So, for x we will write PTQ by 2 and you take 2 to the left hand side, twice angle OPQ is equal to angle PTQ is what we have to prove, what has been asked in the question. So, this is how we prove this, show the this PTQ is equal to twice angle OPQ.